1998, a whole series of developments building the Robonaut1A system. It started out as just a couple subsystems, an arm and a hand. By '99, we'd put the arm and the hand together with a head, and for the first time we experienced dexterous telepresence, where we could really kind of step into this robot and reach out and interact with objects, and in particular EVA tools. And at that point we realized we really had something special, that this capability was possible and that it was within our grasp. The Robonaut1A system evolved over a couple years. We added a second limb. We went upright with a torso and formed what we think of as an upper body for a Robonaut system. Then we commissioned the Robonaut1B unit, where 1A had a lot of electronics in a rack off to the side. 1B's electronics were all integrated in its torso. And that opened up a whole new series of opportunities for making the robot portable, able to move around, not just requiring that work be brought to it, but that it could go to the work and do the work where it sat. We tried a number of lower bodies. There's a picture there of a Robonaut1B with a leg, which would be appropriate for climbing on the outside of the space station, or for on the inside for that matter, plugging into work intersite fixtures. We also tried it on a Segway, and then there's a photo there of a four-wheel base we built called Centaur, which we named based on the fact that it kind of looked like the mythological creature, 4 wheels, not 4 legs, but with the upper body of a human. We took that out to the field and tested it working with natural objects like rocks and geological samples. We learned a lot of things about the upper body, the dexterity, the component technologies, system level redundancy, and made major steps forward in the software. We were partnered with DARPA, the Defense Advanced Research Projects Agency, and teamed with a number of tremendous research partners across the country: USC, MIT, University of Massachusetts, Vanderbilt, Rice, and other universities were all brought in and have contributed in many ways to the Robonaut software. But at the end of this series, we had a number of new ideas, and you could only incrementally upgrade a robot so much. We had some ideas for what Robonaut2 would be, and we went looking for some external funding. If you could go to the next slide. We found a terrific partner in General Motors. They shared our vision for a robot that could do work, real work, and do it safely next to people. Kind of at the core of that idea is that we're not replacing people. It doesn't make any sense to build a robot that can safely work around people if there are going to be no people. It's really predicated on the idea that there will be people working with the robot. They liked that idea. They saw that as a part of their future of combining humans and robots working together, and they agreed to partner with us on the development of the Robonaut2 series. To date, we've built 2 units. R2A is the one here in the room with us today, and R2B is the one that is packed and ready for launch on STS-133. We went through a similar buildup where we built the Robonaut2 limb first, the right arm on R2A, and then we built the second limb and the torso, and then moved on to the second unit, R2B. When we were given the challenge to take a Robonaut2 to station, we selected R2B as the more recent one, and initiated a whole series of tests and then redesign to qualify the R2B system for flight. At the bottom of that slide is a photo of R2, one of the R2 units, in a test chamber out at the White Sands test facility. This was just one of the many tests that the Robonaut system had to go through and pass before being allowed and be certified for use on the space station. In that particular test, the robot was put literally in an oven and baked at 120 degrees for about 4 or 5 days. And at the end of that, the air was extracted from the chamber and sniffed by a computer nose that found very little off-gassing, and the robot passed. It's very important when you put something like Robonaut in an IV environment that you not off-gas, emit chemicals off of the system and pollute the environment. It turns out the Robonaut2s are pretty clean. The Robonaut went through a whole series of additional tests, and it's been a great last 6 months or so getting it certified. Go to the next slide, please. Let me tell you a little bit about the arm. Superficially, it's very smooth and padded. There are no sharps or hard points that could hurt a person. But that's really just the beginning of making a robot safe. At the core, in the muscles of every joint, are springs that make the system compliant. So if you go push on it, it feels soft. So if the robot's minding its own business and just basically turned off, and an astronaut were to bump into it, it would give a little, and it would not injure the astronaut. That's using a series of springs that we developed with sensors capturing the deflection of the springs in a concept called series elastic actuation. We've also developed a way to coordinate those springs, not just through an entire limb, but with two limbs, reaching out and grasping objects in common. Most robots can't do that safely because they're very stiff, and a very slight position error would produce large forces, and the two arms would damage themselves. Because these robots are fundamentally soft, we are able to program them to work together with multiple arms, and in fact work with humans holding the same object. So superficially it's soft, padded, and safe. Mechanically it is soft as well with springs. But deeper than that, it has 3 levels of sensors, electrical sensors, and software that can, in each of the 3 levels, identify forces that are being felt by the robot, decide if those forces are safe or not, and stop the robot. That 3 levels of safety was essential in convincing our payload safety review panel that this robot would be safe to work adjacent to astronauts inside the space station. Each of those 3 levels has a separate sensor pack, separate cable harness going back to a separate process running, monitoring those forces. And if there's ever a problem, the robot can either just stop and wait for the problem to go away, or completely turn itself off. It's programmable so we can have different levels or thresholds at which it will either pause or completely turn off. That is at the core of every motion that the Robonaut system makes, and it gives us confidence that the robot will be safe working around us. I'm going to now play 2 videos, well, a combination of 2 clips. Go to the first video sequence that shows this paradox. We want to have a robot that's both strong enough to do work, and at the same time safe enough to do it right next to us. So the first part of this shows it handling a dumbbell. That's a 20-pound dumbbell. You can relate to what that would feel like if you were to reach out and pick it up. Unlike people, which tend to cheat, this robot will really do what the physical trainers tell you to do, which is to do the bicep curls nice and slow. So as the robot's doing it, because of your empathy and the monkey see, monkey do ability of the human, you can almost feel what that robot is feeling. You know what that would feel like curling that weight, and that's because that's the way humans work. We look at other humans and we can kind of know what it would feel like if we were them. That applies to this robot. It is so human-like. You have a good idea of what the forces are that are involved. You can kind of feel the burn, right, as it's doing that exercise. Humans have greater peak strength and peak speed than a Robonaut 2. Now, for a robot to be your assistant, you really don't want it to move too fast. But a Robonaut has more endurance than a human. While it might not have the same peak strength or peak velocity, it can do things much longer. And that's what you would really want in an assistant. If you asked the robot to hold something and then you were going to work on it for a while, the robot would not complain if you asked it to hold it for 30 minutes in the same position. That is what you'd want in a good assistant. And unlike some people, it will put things back when it's done. Another very useful thing in having an assistant. When you're done with an object, it can put it back for you. So it's strong. You will not see most of the humanoids out there handling 20-pound dumbbells. Most of them don't even really have fingers. They do a lot of dancing, and we're fine with that. We could probably program a Robonaut to do dancing, but we're pretty sure no matter what dance move we would give it, it would always do the robot. For us, it's more about doing work, and that's why we really focused on the upper body. So here it's doing a sequence. It's running through some open space motion. And now Dr. Ron Diffler is going to step into its workspace. We call this the Hit Ron demo. And you see the robot stopped. It paused. It detected that Ron had gotten in the way. And then when he let it go, it continued on with its sequence. While it's pausing, it's applying a very light force. It's trying to catch up. And when it does, it goes back to the motions that it's programmed to do. So this is running at the core of the robot every single time it moves. If a person steps in the way and interferes with it, nothing dangerous is going to happen. The robot will just pause. And if you hit it really hard, it'll stop completely and turn itself off. So we have those two levels of safety. They're always running whenever a Robonaut is in motion, working with our astronauts. So move on to the next slide, please. I'll tell you a little bit about the hands. Within each finger, we've got tendons, and we have force control. We're able to sense tendon forces and map that to finger forces. We also have load cells on every phalange, every finger bone, so we can measure fingertip contact forces. We can also resolve the direction of those contacts, so we can understand and let the robot understand that it's made contact with an object, and even use those fingers kind of like sensors to map out the shape of an object. You'll see how that's important in a minute. We've mapped those tendons and tip force sensors into whole finger control modes that allow the robot to be given different things like a soft grasp or a hard grasp, power grasp, and lots of different shapes of grasps that humans just really take for granted. This hand is a mechanical marvel. It's a mechatronic marvel because it's integrated with electronics as well. It has some things that humans just take for granted but that you don't see in a lot of robot hands. It actually has palms. Most robot hands only have grippers to grab things between fingers. They don't envelop objects and bring them into a palm. The second thing that this robot has that's unusual is a soft covering. We take that for granted. As humans, we have skin, and sometimes we put other layers on called gloves. If you look at most robot hands, they're hard steel fingers. You would not ever want them to grab an object and then have an astronaut grab that object later. If it was an object that was made out of aluminum or steel, those hard fingers might leave a burr or a nick on that object that could later cut the astronaut's glove. What we want is to have a robot that does not cause nicks and burrs in the environment and will be safe to handle the same objects that we'll ask astronauts to handle. The skin is also really important for friction. We can put different kinds of materials in and give the robot's skin, palmar surfaces of the fingers, different levels of, different coefficients of friction to allow it to grasp objects more completely. And also a little cushioning gives some give and allows the robot to have both a very delicate, fine force resolution, yet still be tough enough to really get a white-knuckle grasp on an object. I'm going to show you a couple video clips here that demonstrate how we take advantage of that. So play the next video, please. So this shows the robot hand kind of groping an object. It's a flexible material that's got a bump in it. The robot is basically scanning the object, using its sensors to map out the 3D shape of that object. It wouldn't need to do this every time, but once it's learned the feel of the object, it could apply that. So it grabs the object, it immediately knows where it is, and can now put its thumb in that divot. By having first familiarized itself with the object, it's able to now do that automatically. When it just first makes contact, to immediately know where it is and slide its thumb into position. As far as we know, this is the first robot that has that capability. Okay, next slide, please. Oh, okay. Well, that's fine. We can play this video. So we're now going to talk about the future for the Robonaut system. This is the very recent past. The Robonaut2B system was processed at the Kennedy Space Center, being prepared to be packed in the MPLM. So this is a time-lapse video showing the technicians, both Robonaut engineers and the Kennedy workforce